Here is another puzzle of the same kind. Can you get a state from a different state using a certain kind of moves? This time, instead of birds on trees, you have lamps in a grid. Don't ask me why grid. So we begin with two numbers n and m, which are greater or equal to 3. They're integers. You have a rectangular n by m grid of lamps, so one lamp in each box. Initially, all lamps are off. In a move, you can either flip all lamps in a row or all lamps in a column. And you get to choose which row or which column. So when I say flip, so what does it mean to flip a lamp? It means to turn it on if it was off, and to turn it off if it was on. Assume that initially all NM lamps are off. Can you achieve by a sequence of moves a state where the 4 corner lamps are on, but all other lamps are off? So what do I mean by the corner lamps? So here is an example for n is equals 3 and m equals 4. This is a grid. So this, and this are the 4 corner lamps. So I want them to be on in the end. Of course, as usual, I'm using 0 for off and 1 for on. So here's an example of the flips. So we start with all lamps being off, so zeros everywhere. And then let's flip this column. So 0, 0, 0, it becomes 1, 1, 1. We're turning them all on. And now let's flip this row. So the zeros become zeros, and this 1 becomes a 0 again. So in a way, if you're familiar with modulo 2 computations with a finite field F2, you might recognize a little bit of it, but you can also view it as just a simple combinatorics problem. And again, this is a puzzle worth thinking about, so it's a good occasion to pause and think about it. I'm claiming that the answer is no. And why not? Again, we find an invariant that has one value in the initial state, a different value in the state we desire to get, but however, it is an invariant, so it cannot actually get to a different state by a sequence of moves. So to define this invariant, I'm going to designate 4 certain states, 4 certain cells as special. So the 4 cells on the top, so the 4 cells at the intersection of the topmost 2 rows and the leftmost 2 columns will be called special. So just as an example, here is, if these are all the cells, I'm gonna mark the special cells with asterisks. They're this, and this. So special cells marked with asterisks. So what's special about the special cells? What happens to the special cells, or rather to the special lamps, so the lamps in the special cells, when I make a move? Okay, so one option is that the move flips a row that doesn't contain any of them or a column that doesn't contain any of them. And so their states don't change. So we have the following options. One is that their states don't change. The other is, for example, we flip this column and let's say these 2 special lamps were off. Then they become on. So 2 special lamps that were off are turned on. Another option is that they were on and now become flipped off, so they're turned off now. So two special lamps that were on are turned off. Another option is that one of them was on and the other was off. And the flip just changes the roles. So the one that was on becomes off, the one that was off becomes on. One special lamp that was on is turned off, and another that was off is turned on. These are the only possibilities, because it doesn't matter whether I flip this column or this column or this row or this row. Either of them has exactly two special lamps in it. So I'm gonna be in one of these cases. What do these four outcomes have in common? So in each of these four outcomes, the number of special lamps that are on, it might change, but it preserves its parity. So there we have an invariant. Here the number doesn't change, here the number increases by 2, here it decreases by 2, here it doesn't change because they're just flipping their roles. Okay, so this number is an invariant. Initially it was 0 because no lamp was on. In the final state we desire, it would be 1. So it must change its parity. Okay, sorry, this number is not invariant. The parity of this number is invariant. So initially it was even, namely 0. In the final state, we desire it would be odd, namely 1. So it must change its parity, contradiction. Or rather, so it is impossible to get the desired state. So, little attentiveness question. Where did we use that n and m are bigger or equal to 3? Hint is you can easily find, if n, for example, is 2, you can actually disprove this pretty easily. So you can get all of the four corner lamps to be on. So we actually did use it. The question is where. You have to be attentive on exams. This kind of cases can bite. Now with this exercise solved, let's look a little bit more at this exercise and let's see what else we can say about these lamps. So let's continue studying the lamp grid from this exercise. So we know one configuration that we cannot achieve, but we might wonder what configurations can we achieve and how many. So how many different states, and a state is really just a state is just a determination of which lamps are on and which are off, can we reach using our moves from the initial state in which all lamps are off. So of course there are 2 to the nm states in total, but we already know that not all of them can be reached. How many states can we reach? So again, it's worth thinking about it. Not always do we actually have nice answers to questions like this, but we can always try. So here are some observations. One is that, okay, I need one piece of notation. A line will mean a row or a column. So our grid has n plus m lines, n rows and m columns. And each move flips all lamps in a line. Now, some observations. Flipping a line twice does nothing. Because if you flip a lamp and then flip it again, it's back to where it was before. And of course, the same holds for any given line. Secondly, the order in which we flip lines doesn't matter. It only matters how often we flip a line, not in. So for example, if we flip a row and then a certain column, or if we flip the column first and then the row, we get the same result. Every lamp that is in one of them gets flipped once, and every lamp, then the lamp that is in the intersection gets flipped twice, so it's back. So we only get, so any state that we can reach by flipping every line at most once. If you flip a line more than once, that's just an extra redundant step that we can remove. So since the order doesn't matter, we only need to decide which of the n plus m lines we flip. So we have 2 to the n plus m possibilities. Basically, we get to choose, do we flip this line? 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 Flipping them twice or more is not an option because that would be useless. Flipping them in a different order, the order doesn't matter, so we don't care about the order. 2 to the n plus m possibilities. Does this mean we have 2 to the n plus m possible states? So we can reach 2 to the n plus m states. Nope, because we haven't ruled out the possibility that several possibilities can lead to the same state. And that actually happens. So 2 possibilities might lead to the same state. And this happens because if you flip all the lines, every lamp is getting flipped twice. And that just changes nothing in the long run. Every lamp gets turned on and then off again. For example, flipping all the lines makes no change in total. So less than 2 to the n plus m. Can we do better? Can we be more precise? Well, it turns out that flipping the last column is redundant. If you want to flip the last column, you can instead flip all the other lines. So all the other columns and all the rows. Indeed, the effect of flipping the last column can also be achieved by flipping all the other n plus m minus 1 lines. Thus, we can remove the last column, I mean, not remove it literally, but we can ignore or let me say it this way. When we flip lines, we can avoid flipping the last column. So we have 2 to the n plus m minus 1 possibilities because the last column is no longer part of those possibilities. We've seen that it doesn't actually give us any new states that we couldn't reach otherwise. Now, does this mean we can reach 2 to the n plus m minus 1 states? And this turns out to be a yes. However, it has to be proved. Yes, once we can show that any 2 different possibilities lead to different states. And this I will leave to you. It's a nice little argument. Basically, the idea is, imagine you have some state that you achieved by flipping the rows and all but the last column. How can you reconstruct from the state which rows and which columns you have flipped? So I'm not going to give this proof. The notes have a hint. So there is a hint on proving this in the notes. And we'll see a little bit more of this lamp grid later on. So much for invariance.